Tonight, we embark on a gentle journey outward from our star. Each planet will unfold as its own chapter, and the science will remain clear while the language stays accessible. You can listen actively, let your mind wander, or drift into sleep as we map what lies beyond. Mercury gives way to Venus. Then Earth and Mars appear, followed by the giant worlds and the distant frozen zones. Each destination brings with it recent discoveries. This is not meant to be a catalogue of facts to commit to memory. Instead, think of it as a structured walk where every piece of information finds its place beside a mental image and the rhythm never hurries. We will observe the heat and the cold, examine the gases and the rocks. We will notice how orbital patterns create rhythm and how sunlight shapes the character of each world, all without rushing through the details. When technical terms appear, they will be explained in everyday language before their formal names are introduced. This way, understanding comes first and the terminology follows naturally. By the time we arrive at the far reaches, your mental map of the system will feel complete, and your sense of passing time will have stretched and slowed as the narration moves steadily forward. The journey ahead spans distances almost impossible to grasp through everyday experience. From Mercury, skimming close to the Sun at 58 million kilometers, to the Oort cloud stretching perhaps a light year away, we traverse scales that challenge intuition. Yet each world we encounter follows the same physical laws, shaped by gravity, temperature, and time. The story of the solar system is one of transformation. From a spinning cloud of gas and dust 4.5 billion years ago, gravity sculpted distinct worlds, each bearing the signature of its formation environment. The inner region, hot and bright, became the domain of rock and metal. The outer reaches, cold and dim, allowed ice to persist alongside rock, building larger worlds that could capture hydrogen and helium before the solar wind swept the lighter gases away. This architecture was not predetermined, but emerged naturally from the interplay of physics and chemistry in the early nebula. Before we step onto the first planet, we should pause to consider the Sun itself, the central body that holds everything in orbit. The Sun is a star, a massive sphere of hydrogen and helium undergoing nuclear fusion at its core. Temperatures there reach about 15 million degrees Celsius, hot enough to fuse hydrogen atoms into helium and release tremendous energy. This energy works its way outward over thousands of years, eventually reaching the surface and radiating into space as light and heat. The Sun contains more than 99% of all the mass in the solar system. Its gravity dominates everything within its reach, holding planets, moons, asteroids, and comets in their paths. The visible surface of the Sun, called the photosphere, appears relatively calm from a distance. Up close, it is anything but peaceful. Convection cells the size of countries rise and fall, carrying heat from below. Sunspots appear as dark patches, regions where magnetic fields suppress convection and the surface cools slightly. These spots follow an 11-year cycle, growing more numerous at solar maximum and fading during solar minimum. The cycle reflects changes in the Sun's internal magnetic dynamo, a complex process not yet fully understood. Above the photosphere lies the chromosphere, a thin layer of gas visible during solar eclipses as a reddish glow. Beyond that extends the corona, a halo of superheated plasma reaching millions of degrees. The corona is hotter than the surface beneath it, a fact that puzzled scientists for decades. The heating mechanism likely involves magnetic fields tangling and releasing energy, though the details remain under study. The solar wind flows outward from the corona, a stream of charged particles that fills the solar system. This wind shapes the magnetospheres of planets and pushes comet tails away from the Sun. It also defines the boundary of the heliosphere, the bubble of space under the sun's influence. Solar flares and coronal mass ejections are dramatic events where magnetic energy releases suddenly. Flares produce bursts of radiation across the electromagnetic spectrum. Coronal mass ejections hurl billions of tons of plasma into space. When these phenomena are directed toward Earth, they can disrupt satellites, power grids, and communications. Auroras become more intense and visible at lower latitudes. Understanding space weather is increasingly important as our technology becomes more interconnected and vulnerable. The Sun formed about 4.5 billion years ago from a collapsing cloud of gas and dust. Gravity pulled material inward, heating the core until fusion ignited. The remaining disk of material around the young Sun gave rise to planets, moons, and smaller bodies. This process is common throughout the galaxy. We now observe similar disks around other young stars, watching planetary systems in the act of formation. Each observation refines our understanding of how our own system began. The earliest stages of planet formation involved dust grains colliding and sticking together through electrostatic forces. These grains grow into pebbles, then boulders, and eventually kilometer-sized bodies called planetesimals. Gravity becomes dominant at this scale, allowing rapid growth through collisions. Within a few million years, dozens of Moon-to-Mars-sized planetary embryos formed. These embryos continued colliding, their impacts generating tremendous heat. Some melted entirely, allowing heavier elements like iron to sink toward the center while lighter materials floated upward. This process, called differentiation, created the layered structures we see in rocky planets today. The Sun is not eternal. It has already consumed about half of its hydrogen fuel. In roughly 5 billion years, it will exhaust the hydrogen in its core and begin fusing hydrogen in a shell around an inert helium core. The Sun will swell into a red giant, expanding beyond the orbit of Mercury and possibly Venus. Earth will be scorched, its oceans boiled away. Eventually, the Sun will shed its outer layers, creating a planetary nebula. The core will collapse into a white dwarf, a dense remnant that will slowly cool over trillions of years. This is the fate awaiting our star, though it lies so far in the future that it feels abstract. For now, the Sun remains stable, a steady provider of light and warmth. Studying the Sun requires specialized instruments that can observe across many wavelengths. Ground-based telescopes equipped with solar filters capture visible light, revealing sunspots and granulation patterns. Space-based observatories like the Solar Dynamics Observatory monitor the Sun constantly, tracking changes in ultraviolet and extreme ultraviolet light. These wavelengths reveal activity in the corona and chromosphere that is invisible from Earth's surface. The Parker Solar Probe, launched in 2018, is flying closer to the Sun than any previous spacecraft. It passes through the corona itself, measuring magnetic fields, plasma properties, and particle velocities directly. The data are helping to solve long-standing mysteries about coronal heating and solar wind acceleration. The Sun's energy output varies slightly over the 11-year cycle, but these variations are small. More significant are the long-term changes that occur over millions of years as the Sun gradually brightens. Early in Earth's history, the Sun was about 30% dimmer than today. This faint young Sun paradox raises questions about how Earth remained warm enough for liquid water. The answer likely involves higher concentrations of greenhouse gases in the early atmosphere. As the Sun brightens slowly over billions of years, Earth's climate will continue to change unless counterbalanced by natural or artificial processes. Solar eclipses have played important roles in astronomy. During a total solar eclipse, the Moon blocks the Sun's bright disk, allowing the faint corona to become visible. Observations during eclipses have led to discoveries about the Sun's outer atmosphere and have even provided tests of general relativity. The 1919 eclipse expedition confirmed that starlight bends near the Sun, matching Einstein's predictions and bringing relativity to public attention. Today, eclipses remain opportunities for scientific study and public engagement, reminding us of the celestial mechanics that govern our system. From the Sun's perspective, the planets are tiny specks scattered across vast emptiness. The inner solar system, where the rocky planets orbit, is bathed in intense light and heat. Here, temperatures are high enough that only metals and rocks can remain solid. Farther out, beyond a boundary we call the frost line, temperatures drop low enough for water ice to form. This division shaped what kinds of planets formed where. Rocky worlds close in, icy giants farther out. The architecture is not accidental, but a consequence of temperature, chemistry, and gravity working together over millions of years. The frost line sits roughly where the asteroid belt is today, between Mars and Jupiter. Inside this boundary, water existed only as vapor, unable to condense. Outside, water ice added significant mass to forming planets, allowing them to grow much larger. This explains why Jupiter and Saturn are so massive compared to Earth and Venus. The ice also provided a sticky material that helped particles clump together more efficiently. The location of the frost line was not fixed, but moved over time as the young sun's luminosity changed. This migration may have influenced where different types of planets ended up. We begin with Mercury, the world closest to our Sun. It is a compact sphere composed of ancient rock, a traveller moving so swiftly that one full orbit takes only 88 Earth days. With almost no atmosphere surrounding it, Mercury experiences temperature extremes that surpass anything we know. Its surface bears the lasting marks of that harsh exposure. During the day, temperatures can soar well above 400 degrees Celsius, while at night they can drop far below freezing. No thick blanket of air exists to hold warmth. The contrast is absolute. Across this brutal range lies a terrain covered in craters, with overlapping circular rims and sharp edges that remain well preserved. The landscape reads like an ancient record frozen in stone. The cratering on Mercury tells a story of bombardment that spans billions of years. The largest impacts occurred early in the solar system's history, during a period called the Late Heavy Bombardment. Asteroids and comets rained down on the inner planets, leaving scars that remain visible today. On worlds with active geology or thick atmospheres, these ancient craters are erased or buried. Mercury, with neither, preserves them. Each crater represents a moment of violent collision when an object travelling at tens of kilometers per second struck the surface. The kinetic energy converted instantly to heat, vaporizing rock and excavating material. The debris fell back in circular patterns, creating the rims and ejector blankets we see today. Smaller impacts continue to pepper Mercury's surface. Micrometeorites constantly sandblast exposed rocks, grinding them into fine dust over millions of years. This process, called space weathering, gradually darkens the surface. Fresh craters appear brighter because they expose unweathered material from below. Studying crater densities allows scientists to estimate the ages of different regions. Heavily cratered areas are ancient, dating back 4 billion years or more. Smooth plains with few craters are younger, perhaps only a few billion years old. Mercury rotates in an unusual pattern, locked in what is called a 3-to-2 resonance. This means it spins 3 times on its axis for every 2 trips around the Sun. The result is a sky unlike any other in the solar system. If you could stand on Mercury at certain locations, you would watch the Sun rise slowly, come to a stop, drift slightly backward, and then continue forward again. This pattern repeats across extraordinarily long days. A single solar day on Mercury lasts 176 Earth days. The sunlight moves according to a schedule that feels heavy and strange, and the surface endlessly cycles between scorching heat and freezing cold. This is the first insight into Mercury. Time and temperature behave with extreme severity. Motion traces unusual patterns across the sky. The underlying geometry is precise and unforgiving. The 3-2 resonance is not random, but arose from tidal interactions with the Sun. As Mercury's orbit is elliptical, the gravitational pull from the Sun varies throughout each orbit. Over millions of years, this variation slowed Mercury's rotation and locked it into the current pattern. The resonance is stable, meaning small perturbations will not easily break it. This type of orbital dynamics appears elsewhere in the solar system. Many moons are tidally locked to their planets in 1-to-1 resonances, always showing the same face. Mercury's 3-to-2 resonance is less common, but equally fascinating. The Messenger spacecraft entered orbit around Mercury in 2011 and spent 4 productive years mapping its surface and chemistry. The mission transformed our understanding of this small world. Messenger revealed smooth volcanic plains that had filled older impact basins. It discovered long cliff-like formations called lobate scarps. These features stretch across the crust for hundreds of kilometers. The scarps record a global shrinking process. As Mercury's large iron core cooled over time, the outer crust wrinkled and compressed. The entire planet decreased in radius by several kilometers. Messenger also found bright, shallow depressions called hollows. These irregular features appear freshly carved and likely formed as volatile materials escaped from the surface. The process may still be active today. At the point directly opposite the giant Caloris Basin, Messenger captured images of jumbled, chaotic terrain. Fractured blocks and tilted surfaces appear as if they were shaken and tossed. The most likely explanation is seismic focusing from the massive impact that created Caloris. The basin itself is a vast impact structure stretching more than 1,000 kilometers across. Its rings and fractures speak to the violence of the early solar system. The plains surrounding Caloris later filled with flowing lava. The chemistry of those plains revealed unexpected sulfur levels and a surprisingly high abundance of volatile elements for a world so close to the Sun. These findings forced scientists to revise ideas about how Mercury formed. Rather than being completely baked into sterility, Mercury retained certain lighter elements. This persistence challenges simpler thermal models. The nuances matter. One of the most surprising discoveries was the detection of water ice at Mercury's poles. The ice is locked inside shadowed crater floors where sunlight never reaches and temperatures remain perpetually below freezing. Radar reflections had hinted at this possibility years earlier, but Messenger's neutron and laser instruments confirmed the case. The data also revealed evidence of dark organic material mixed with the ice. The deposits appear relatively young. Comets and asteroids likely delivered the water, and subsequent chemical processes stabilized the layers within these permanent shadows. These small, cold traps became reservoirs. It is a striking contrast. Searing heat near the equator at noon, and frozen water hidden in darkness on a world pressed so near the Sun. The lesson here is about geometry and tilt. The discovery of ice on Mercury raises questions about resources for future missions. Water ice can be broken down into hydrogen and oxygen, providing both breathable air and rocket fuel. If humans ever visit Mercury, these polar deposits could be valuable. However, accessing them would be challenging. The poles are difficult to reach, and extracting material from deep within shadowed craters would require specialized equipment. Still, the presence of ice expands the possibilities for exploration. Mercury possesses a global magnetic field, which is rare among small rocky planets. The field is offset slightly toward the north, and this asymmetry affects how the solar wind interacts with the planet. The magnetic field creates a miniature magnetosphere, complete with a tail that is swept back by the flow from the sun. Measurements have detected dynamic reconnection events. Solar wind particles can strike the surface and knock loose atoms, feeding a thin exosphere made of sodium, potassium, and calcium. These atoms glow faintly under certain lighting conditions. A long sodium tail sometimes extends away from the planet, and observers on Earth have captured images of it during specific alignments. This shows that Mercury is not a dead, inactive world. The planet's core occupies a much larger fraction of its interior compared to Earth's core. It is likely composed mostly of iron, with some lighter elements dissolved within. The outer portion of the core remains partially molten. That liquid layer contributes to the magnetic field, and the slow cooling of the interior drives the ongoing contraction visible in the surface scarps. The structural story connects the crust directly to the core. Several formation scenarios remain under consideration. Possibilities include a giant impact that stripped away lighter material, hit-and-run collisions, or sorting of metals early in the solar nebula. Each scenario can explain parts of the observational data. Messenger's geochemical results favor a complex history involving multiple events. Carbon may have migrated upward to form a graphite-rich layer near the surface. This could explain why Mercury's reflectance is so low. Relativity enters the picture through Mercury's orbit. Its closest approach to the Sun, called perihelion, advances slightly faster than Newtonian physics predicts. This small discrepancy was resolved by Einstein's theory of general relativity, which describes gravity as a curvature of space-time. The numbers match observations precisely. This tiny effect became an important test of the theory, turning Mercury into a precise tool for measuring gravitational physics. Its orbital path continues to agree with general relativity. Planetary ephemerides still include Mercury's gravitational influence, and the data help refine solar parameters. Navigation systems benefit from these improvements. A small world can carry profound meaning. Mercury's steady motion continues to teach us about physics with every orbit, and that is worth recognizing. From Earth, Mercury is often difficult to observe because it never wanders far from the Sun in our sky. Twilight tends to wash out its faint point of light. A few times each century, Mercury passes directly in front of the solar disk in an event called a transit. It appears as a tiny moving dot. With safe solar filters, the geometry becomes elegantly visible. These events serve as precise clocks, linking orbital inclinations to predictable dates. The spectacle is both simple and exact. For casual observers, morning and evening elongations provide the best viewing opportunities. A clear horizon to the west or east helps considerably, and patience is rewarded. Bepi Colombo, a joint mission from the European Space Agency and the Japan Aerospace Exploration Agency, is currently on its way to Mercury. The mission involves multiple flybys before entering orbit, planned for 2025. Two spacecraft will then separate for coordinated studies. The mission will refine maps of the surface, study the exosphere and magnetic tail, and measure the gravity field to understand interior structure. The instruments surpass those aboard Messenger, offering better spectral coverage and improved resolution. Bepi Colombo will measure elemental abundances, surface textures, and magnetic fields with higher precision. Models will be refined accordingly. Every new pass adds constraints on how Mercury formed, and each improved measurement narrows the range of possibilities. Science advances through these quiet, careful steps. Mercury's geology reads like a record written in layers of time. Older, cratered highlands and younger, smooth plains tell different stories. Lava once flowed through fractures to fill low-lying areas. Pyroclastic vents mark locations where explosive volcanism occurred. Volatile, rich magma ejected fragmented rock, and dark halos still surround several source pits. The hollows likely represent the loss of volatiles, perhaps sulfur-bearing minerals or chloride compounds heated by sunlight and released slowly over time. The combination of these features suggests a dynamic past despite the planet's small size. Understanding Mercury teaches lessons about planetary evolution under extreme conditions. As we leave Mercury behind, we carry with us an appreciation for extremes. A world where a single day stretches across 2 full years, where ice can exist steps away from zones hot enough to melt lead, where a small planet reveals complex geology and a magnetic personality. Mercury is the first chapter, and it sets a tone of careful observation and respect for detail. The journey continues outward, and the next stop brings us to a very different kind of world. The space between Mercury and Venus is relatively empty, yet it marks an important transition. Venus orbits at nearly twice Mercury's distance from the Sun. The difference in solar heating is significant. Where Mercury bakes under intense radiation, Venus receives less direct energy, yet manages to trap and amplify what it does receive. This demonstrates an important principle. Distance from the Sun matters, but it is not the only factor determining a planet's climate. Atmospheric composition and thickness play equally crucial roles. Venus stands as proof that a planet can become hotter than worlds closer to the Sun if conditions allow heat to accumulate rather than radiate away. Venus waits next, wrapped in thick clouds that never part. From a distance, it appears smooth and bright, reflecting sunlight with intensity. It is nearly the same size as Earth, and, for a time, people imagined it might be similar beneath the haze. Instead, Venus turned out to be one of the most hostile places in the solar system. The surface temperature averages around 465 degrees Celsius, hot enough to melt lead. The atmospheric pressure at ground level is more than 90 times that of Earth, equivalent to the pressure found deep underwater. The atmosphere is composed mostly of carbon dioxide, with clouds of sulfuric acid drifting high above. This combination creates a runaway greenhouse effect that traps heat with relentless efficiency. The greenhouse effect on Venus operates through a simple mechanism repeated to extremes. Carbon dioxide allows visible sunlight to reach the surface, where it is absorbed and re-emitted as infrared radiation. The carbon dioxide molecules absorb this infrared light, trapping the heat. On Earth, this process warms the planet by about 33 degrees Celsius, making it habitable. On Venus, the effect is amplified to the point where surface temperatures exceed those on Mercury. Despite Venus being much farther from the Sun, the thick atmosphere acts as an insulating blanket from which heat cannot escape. Venus rotates slowly and in the opposite direction compared to most planets. A single day on Venus, measured from one sunrise to the next, takes 117 Earth days. Yet one orbit around the Sun takes 225 Earth days. This means that a Venusian day is longer than its year. The slow backward spin produces unusual dynamics in the atmosphere. High-altitude winds race around the planet in just 4 Earth days, a phenomenon called superrotation. The mechanism that drives this remains a topic of active research. Despite the scorching surface, Venus has a relatively young appearance. Radar mapping by missions like Magellan revealed volcanic plains, shield volcanoes, and peculiar dome-like structures called pancake domes. Large coronae, circular features surrounded by ridges and fractures, suggest upwelling plumes of hot material from the interior. The average surface age is estimated at several 100 million years, which is geologically recent. This suggests that volcanic activity resurfaced much of the planet in the not-too-distant past. The Soviet Venera program achieved remarkable feats by landing probes on Venus. Several landers survived long enough to send back images and measurements from the surface. The photographs show flat, rocky plains strewn with angular slabs. The sky appears a dim orange glow even during the day, as thick clouds filter the sunlight. The equipment functioned for only brief periods before succumbing to the heat and pressure. Those fleeting minutes provided the only direct glimpses of the Venusian surface. Volcanic activity on Venus may still be ongoing. Recent observations detected variations in sulfur dioxide levels in the atmosphere, which could indicate fresh eruptions. Infrared data have identified potential hotspots that suggest recent lava flows. Confirming active volcanism requires more observation, but the evidence is suggestive. If Venus is still geologically active, it would help explain why its surface appears so young. The lack of a magnetic field is another notable feature. Venus likely has an iron core, but it spins too slowly to generate a dynamo effect. Without a magnetic field, the solar wind interacts directly with the upper atmosphere, stripping away particles over time. This process may have contributed to the loss of any water Venus once possessed. Early in its history, Venus might have had oceans, but the greenhouse effect intensified, causing the water to evaporate. Ultraviolet light from the sun then split water molecules, and hydrogen escaped into space, while oxygen reacted with surface rocks. Today, Venus is almost entirely dry. The thick atmosphere creates powerful atmospheric tides and unusual circulation patterns. Heat from the surface warms the air, causing it to rise. At higher altitudes, the air cools and circulates toward the poles, then descends. This creates massive convection cells. The clouds form distinct layers, with the highest clouds made of sulfuric acid droplets. Lightning has been detected in the atmosphere, though the exact mechanisms remain under study. The planet's slow rotation affects how energy is distributed, creating unique weather patterns not seen elsewhere. Venus and Earth are often called sister planets because of their similar sizes and densities, yet their climates could not be more different. This divergence teaches important lessons. Small differences in initial conditions, particularly the amount of water and the distance from the Sun, can lead to dramatically different outcomes over billions of years. Earth ended up with liquid oceans and a moderate climate. Venus became a furnace. Understanding why this happened helps scientists model other planetary systems and assess the habitability of exoplanets. Not every Earth-sized world in a star's habitable zone will be friendly to life. The balance is delicate, and many factors must align. Comparing Earth and Venus reveals the importance of feedback loops in climate systems. On Earth, carbon dioxide levels are regulated by the carbon cycle. Rain dissolves carbon dioxide, forming carbonic acid that weathers rocks. Rivers carry dissolved minerals to the ocean, where they precipitate as carbonates. Plate tectonics recycles these carbonates through subduction and volcanism. This cycle acts as a thermostat, stabilizing temperature over geological time. Venus lacks plate tectonics and liquid water, so this regulatory mechanism does not function. Once the greenhouse effect began, nothing stopped it from running away. The water evaporated, the hydrogen escaped, and carbon dioxide accumulated with no removal process. The question of whether Venus ever had oceans remains open. Some models suggest that early Venus could have been habitable for 1 billion years or more before the runaway greenhouse took hold. If true, this window might have allowed life to emerge. Whether that life could have survived the transition to current conditions is unknown. Some scientists speculate that microbes might persist in the cloud layers, where temperatures and pressures are more moderate. This idea is controversial but not impossible. Future missions will search for chemical signs of life, though distinguishing biological from geological processes will be challenging. Venus transits across the face of the Sun are rare and come in pairs separated by 8 years. The last pair occurred in 2004 and 2012. The next will not happen until 2117. Historically, these transits were important for measuring the distance from Earth to the Sun, a value called the astronomical unit. Observers stationed at different locations on Earth timed the transit precisely, and trigonometry provided the distance. Though we now have more accurate methods, the transits remain events of historical and cultural significance. They remind us of the ingenuity used by earlier astronomers to map the solar system. Future missions to Venus are in development. Several space agencies are planning orbiters and atmospheric probes. NASA's Veritas mission aims to create high-resolution topographic maps and study the planet's geology. The European Space Agency's Envision will focus on the interior structure and volcanic activity. India's space agency has proposed an orbiter as well. These missions will help answer lingering questions about Venus's past and present. Did Venus ever have liquid water? Is there active volcanism today? What drives the super-rotating winds? Each question connects to broader themes about planetary evolution and habitability. Despite its harsh conditions, some scientists have speculated about life in the Venusian clouds. High in the atmosphere, temperatures and pressures are less moderate. Liquid droplets could potentially harbour microbial life, shielded from the surface heat. The idea remains speculative, but it is not entirely without merit. Chemical signatures that are difficult to explain have been detected in the atmosphere, though none have been confirmed as biological. The debate continues, and future missions may provide clearer answers. Venus teaches us about runaway climates and the fragility of planetary habitability. A world nearly identical in size to Earth became a furnace due to slight differences in distance from the Sun and atmospheric composition. Understanding Venus helps us appreciate the delicate balance that makes Earth livable. It also informs our search for habitable exoplanets. Not all Earth-sized worlds will be friendly to life. Conditions matter as much as size. As we move away from Venus, we carry lessons about heat, pressure, and atmospheres. A planet can be similar in structure, yet entirely different in character. The next destination is familiar. It is home. Earth appears next in the sequence, a world of oceans, continents, and life. It is the only planet we know with certainty that hosts biology, and it serves as the reference point for everything else we study. Water defines Earth in ways that extend beyond the obvious presence of oceans. The water cycle connects atmosphere, land, and sea in continuous circulation. Water evaporates from the oceans, rises into the atmosphere, condenses into clouds, and falls as precipitation. Rivers carry it back to the sea, completing the cycle. This circulation distributes heat around the planet, moderates temperature extremes, and shapes weather patterns. Water also enables plate tectonics by lubricating the movement of crustal plates. It dissolves minerals, transports nutrients, and provides the medium in which life thrives. Without water, Earth would be unrecognizable. Earth orbits the Sun at an average distance of about 150 million kilometers, a distance we call 1 astronomical unit. This places it in the habitable zone, where temperatures allow liquid water to exist on the surface. Water covers roughly 71% of the planet, creating vast oceans that regulate climate and support life. The remaining 29% is land, divided into continents and islands. The atmosphere is composed mostly of nitrogen and oxygen, with trace amounts of other gases. This mixture is breathable for many forms of life and helps moderate temperature swings. Earth's rotation creates a cycle of day and night every 24 hours. The tilt of its axis, about 23.5 degrees, produces seasons as the planet orbits the Sun. During part of the year, the northern hemisphere tilts toward the Sun, creating summer there, while the southern hemisphere experiences winter. 6 months later, the situation reverses. This tilt drives weather patterns and influences ecosystems. It is a simple geometric fact with profound consequences. Earth has a strong magnetic field generated by the motion of molten iron in its outer core. The field extends far into space, forming a protective bubble called the magnetosphere. This shield deflects most of the charged particles in the solar wind, preventing them from stripping away the atmosphere. Auroras occur when some particles manage to enter near the poles, interacting with atmospheric gases and producing glowing curtains of light. The planet's interior is divided into layers. The solid inner core is surrounded by the liquid outer core. Above that lies the mantle, a thick layer of hot, slowly flowing rock. The outermost layer is the crust, which is broken into large plates. These tectonic plates move slowly over time, driven by convection in the mantle. Where plates collide, mountains form and earthquakes occur. Where they pull apart, new crust is created at mid-ocean ridges. This dynamic system continuously reshapes the surface. Plate tectonics plays a key role in regulating Earth's climate. Volcanic activity releases carbon dioxide into the atmosphere, while weathering and the formation of carbonate rocks remove it. This balance has helped keep temperatures stable over geological time. Without plate tectonics, Earth might have become more like Venus, with a thick carbon dioxide atmosphere and runaway heating. Earth's ocean currents form a global circulation system that distributes heat around the planet. Warm water from the tropics flows toward the poles, while cold water from the poles returns toward the equator. This thermohaline circulation is driven by differences in temperature and salinity. The Gulf Stream, for example, carries warm water from the Caribbean northward along the eastern coast of North America and across the Atlantic toward Europe. This current moderates the climate of Western Europe, making it warmer than it would otherwise be at such high latitudes. Changes in ocean circulation can have significant climate impacts. During past ice ages, shifts in currents affected global temperatures and precipitation patterns. The atmosphere is organized into distinct layers. The troposphere, where weather occurs, extends from the surface to about 10 kilometers. Above that lies the stratosphere, which contains the ozone layer that absorbs harmful ultraviolet radiation. Higher still are the mesosphere, thermosphere, and exosphere. Each layer has different temperature and composition characteristics. The boundaries between layers are marked by temperature inversions, where the trend of increasing or decreasing temperature reverses. Life on Earth is extraordinarily diverse, ranging from microbes in deep-sea vents to trees in rainforests, from whales in the oceans to birds in the sky. All known life shares a common chemistry based on carbon, water, and complex molecules. The origin of life remains one of the great mysteries. It likely began in the oceans more than 3.5 billion years ago, possibly near hydrothermal vents where chemical energy was abundant. Over time, simple organisms evolved into more complex forms. Photosynthesis developed, allowing organisms to harness sunlight and produce oxygen. This transformed the atmosphere and paved the way for more complex life. The Great Oxidation Event, which occurred around 2.5 billion years ago, represents one of the most dramatic transformations in Earth's history. Before this event, the atmosphere contained little free oxygen. Cyanobacteria, photosynthetic microorganisms, began producing oxygen as a waste product. At first, the oxygen reacted with dissolved iron in the oceans, creating rust-colored sediments that settled to the seafloor. These banded iron formations are visible in ancient rock layers today. Eventually, the oxygen began accumulating in the atmosphere. This was initially catastrophic for many anaerobic organisms, which found oxygen toxic, but it also opened new possibilities. Oxygen-breathing organisms could extract more energy from food, enabling the evolution of larger, more complex life forms. The event reshaped the planet and set the stage for everything that followed. Earth's biosphere interacts closely with the atmosphere, oceans, and land. Plants absorb carbon dioxide and release oxygen. Decomposers break down dead material, recycling nutrients. Predators and prey maintain population balances. These interactions create ecosystems that can be remarkably stable, yet also vulnerable to disruption. Human activity has significantly altered the planet in recent centuries. Deforestation, fossil fuel combustion, and industrial processes have increased atmospheric carbon dioxide levels. This has led to global warming and changes in climate patterns. Ocean acidity is rising as excess carbon dioxide dissolves in seawater. Ice sheets in Greenland and Antarctica are melting, contributing to sea level rise. These changes pose challenges for ecosystems and human societies alike. The diversity of Earth's biomes reflects variations in climate, geography, and evolutionary history. Tropical rainforests near the equator receive abundant rainfall and warmth year-round, supporting dense vegetation and a staggering variety of species. Deserts, found in regions with little precipitation, host organisms adapted to conserve water and withstand temperature extremes. Temperate forests experience distinct seasons, with trees shedding leaves in winter and regrowing them in spring. Grasslands support large herds of herbivores and the predators that hunt them. Tundra, found at high latitudes and high altitudes, is characterized by permafrost and low-growing plants. Each biome represents a different solution to the challenge of survival under specific environmental conditions. Studying Earth from space has provided new perspectives. Satellites monitor weather patterns, track deforestation, measure sea ice extent, and observe atmospheric composition. These tools help scientists understand how the planet functions as a system. They also reveal the interconnectedness of different processes. A volcanic eruption can affect global temperatures. Ocean currents influence regional climates. Changes in one part of the system ripple outward. The Moon orbits Earth at an average distance of about 384,000 kilometers. It formed roughly 4.5 billion years ago, likely from debris ejected after a Mars-sized object collided with the young Earth. The Moon's gravity affects Earth in several ways. It stabilizes the axial tilt, preventing large variations that could cause extreme climate shifts. It also creates tides in the oceans. The gravitational pull of the Moon causes water to bulge on the side facing it and on the opposite side. As Earth rotates, these bulges move, creating the rise and fall of tides. Over time, tidal forces have slowed Earth's rotation and pushed the Moon farther away. The Moon is currently receding at a rate of about 4 centimeters per year. The Moon is tidally locked to Earth, meaning the same side always faces us. The near side is familiar, with its dark maria, or seas, which are actually ancient lava plains. The far side remained hidden until spacecraft photographed it in the 1960 seconds. It is heavily cratered and lacks the large maria found on the near side. This asymmetry may be due to differences in crustal thickness or the distribution of heat-producing elements. The Moon has no atmosphere and no magnetic field. Its surface is covered in a layer of fine dust called regolith, created by billions of years of micrometeorite impacts. Temperatures swing wildly from over 100 degrees Celsius in sunlight to below -150 degrees in shadow. The Apollo missions returned hundreds of kilograms of lunar rocks and soil. Analysis of these samples revealed that the Moon is made of material similar to Earth's mantle, supporting the giant impact hypothesis. The samples also showed that the Moon has been geologically inactive for billions of years. The last volcanic activity occurred around 1 billion years ago. Since then, the Moon has been a cold, dead world, its only changes coming from impacts. Recent missions have discovered water ice in permanently shadowed craters near the lunar poles. This ice could be a valuable resource for future human exploration, providing drinking water and material for producing rocket fuel. Plans are underway to return humans to the Moon through NASA's Artemis program. The goal is to establish a sustainable presence, using the Moon as a testing ground for technologies needed for Mars missions. Lunar bases could serve as laboratories, manufacturing centers, and waypoints for deeper space exploration. Human exploration of space began with Earth orbit and later extended to the Moon. The Apollo program landed 12 astronauts on the lunar surface between 1969 and 1972. They collected samples, conducted experiments, and demonstrated that humans could live and work in space. Since then, space stations like Mir and the International Space Station have provided platforms for long-duration missions. Astronauts have studied the effects of microgravity on the human body, tested technologies, and conducted scientific research. These experiences will inform future missions to Mars and beyond. Earth is unique in the solar system as the only world with abundant liquid water, a breathable atmosphere, and thriving life. Yet it is also fragile. Maintaining its habitability requires understanding the processes that sustain it and taking care to minimize harm. As we prepare to move outward to other worlds, we carry with us the knowledge gained here. Earth serves as both home and laboratory, teaching us what makes a planet livable. Leaving Earth behind, we continue outward to Mars, the red planet. It has captured human imagination for centuries. Its reddish colour comes from iron oxide, or rust, in the surface soil. Mars is roughly half the diameter of Earth and has about 1/10 of Earth's mass. Its gravity is weaker, about 38% of what we experience on Earth. The thin atmosphere is composed mostly of carbon dioxide, with surface pressure less than 1% of Earth's. This makes the environment harsh and inhospitable to life as we know it. Mars has a day length very similar to Earth's, lasting about 24 hours and 37 minutes. Its axial tilt is also comparable to Earth's, at about 25 degrees. This produces seasons, though they are nearly twice as long because Mars takes 687 Earth days to orbit the Sun. The northern and southern hemispheres experience opposite seasons, and dust storms can grow to cover the entire planet. These storms are driven by temperature differences and can last for months. The global dust storms on Mars are spectacular yet predictable phenomena. They tend to occur when Mars is near perihelion, its closest approach to the Sun. The extra heating stirs up winds that lift dust from the surface. Once aloft, the dust absorbs more sunlight, heating the atmosphere further and creating even stronger winds. The process feeds on itself until dust blankets the entire planet. These storms can obscure the surface for weeks or months. They pose challenges for solar-powered rovers, but also provide opportunities to study atmospheric dynamics on a global scale. The storms eventually dissipate as dust settles back to the surface, and the cycle begins anew years later. The surface of Mars is diverse. The northern hemisphere consists mostly of low-lying plains, while the southern hemisphere is heavily cratered and sits at a higher elevation. This dichotomy is one of the planet's defining features. Olympus Mons, the largest volcano in the solar system, rises about 22 kilometers above the surrounding plains. It is a shield volcano, formed by repeated lava flows over millions of years. Nearby, the Tharsis region contains several other large volcanoes and a massive system of canyons called Valles Marineris. This canyon stretches more than 4,000 kilometers and reaches depths of up to 7 kilometers in places. It dwarfs the Grand Canyon on Earth. Dust devils are common on Mars, visible as dark swirling columns that move across the surface. These vortices form when sunlight heats the ground, causing warm air to rise rapidly. As the air spirals upward, it lifts dust from the surface, creating a visible funnel. Dust devils on Mars can be much larger than those on Earth, reaching heights of several kilometers. They play a role in redistributing dust across the planet and have occasionally cleaned solar panels on rovers, extending mission lifetimes. The Martian polar caps are composed of water ice and frozen carbon dioxide. During winter, in each hemisphere, carbon dioxide from the atmosphere freezes out onto the polar cap, causing it to grow. In summer, the carbon dioxide sublimates back into the atmosphere and the cap shrinks, revealing a permanent residual cap of water ice beneath. The southern polar cap sits atop a thick deposit of layered terrain, which likely records climate variations over millions of years. Studying these layers could provide insights into Martian climate history, much like ice cores on Earth reveal past terrestrial climates. Mars shows abundant evidence of past water. Ancient river valleys, lake beds, and deltas have been identified from orbit. Minerals that form in the presence of water, such as clays and sulfates, have been detected by rovers. These findings suggest that Mars once had a thicker atmosphere and a warmer, wetter climate. Liquid water may have flowed on the surface for extended periods billions of years ago. Understanding what happened to that water is a key question. Some was lost to space, stripped away by the solar wind after Mars lost its global magnetic field. Some remains locked in polar ice caps and underground deposits. Recent discoveries indicate that liquid brines might occasionally flow on steep slopes during warmer months, though the evidence remains debated. Mars has two small moons, Phobos and Deimos. Both are irregularly shaped and likely captured asteroids. Phobos orbits close to Mars and is slowly spiraling inward due to tidal forces. In several million years, it will either break apart or crash into the surface. Deimos orbits farther out and is gradually moving away. Both moons are heavily cratered, and their surfaces are covered in a layer of fine dust. The history of Mars observation stretches back centuries. Ancient astronomers noted its reddish colour and its wandering path across the sky. In the late 19th century, observations through telescopes suggested the presence of linear features, which some interpreted as canals built by an advanced civilization. This sparked widespread interest in the possibility of Martian life. The canals turned out to be optical illusions, but the fascination with Mars persisted. In the 20th century, robotic missions began visiting Mars, revealing a world very different from the imaginings of earlier generations. The first successful Mars mission was Mariner 4, which flew past the planet in 1965 and returned images of a cratered, moon-like surface. Later missions showed a more complex picture, with evidence of ancient water and volcanic activity. The Viking landers in the 1,970 seconds conducted experiments searching for life, but returned inconclusive results. The debate over their findings continues to this day. In recent decades, Mars has become one of the most studied bodies in the solar system, with multiple orbiters, landers, and rovers active simultaneously. Robotic exploration of Mars began in the 1,960 seconds, and the pace has accelerated in recent decades. NASA's Curiosity and Perseverance rovers are currently active on the surface. Curiosity has been exploring Gale Crater since 2012, studying sedimentary layers and measuring radiation levels. Perseverance landed in Jezero Crater in 2021 and is collecting samples that may be returned to Earth by a future mission. It also carries an experiment to produce oxygen from atmospheric carbon dioxide, a technology that could support future human missions. The Ingenuity helicopter accompanied Perseverance and demonstrated that powered flight is possible in the thin Martian atmosphere. It completed dozens of flights, far exceeding its expected lifespan, and scouted terrain for the rover. Orbiters around Mars have mapped the surface in great detail. They have identified mineral deposits, tracked weather patterns, and detected seasonal changes in ice cover. Instruments have measured the planet's gravity field, helping scientists understand the internal structure. Mars has a partially molten core, but no global magnetic field remains. Localized crustal magnetic fields in the southern highlands suggest Mars once had a dynamo that later shut down. The search for life on Mars is a central goal of exploration. While the surface is too harsh for known life forms, subsurface environments might be more hospitable. If liquid water exists underground, it could provide a habitat for microbes. Methane has been detected in the Martian atmosphere, and its levels vary with the seasons. Methane can be produced by geological processes or by biological activity. Identifying its source is a priority. Future missions will drill deeper into the surface, searching for organic molecules and signs of past or present life. Mars Sample Return, a collaborative effort between NASA and the European Space Agency, aims to bring Martian rocks and soil back to Earth. Laboratory analysis of these samples could answer questions that rovers cannot address in the field. Plans for human missions to Mars are advancing. NASA's Artemis program aims to return humans to the Moon and use it as a stepping stone for Mars exploration. The challenges are significant. The journey takes 6 to 9 months each way, and astronauts would need to live on Mars for an extended period before the return launch window opens. Life support systems must be reliable. Radiation exposure during transit and on the surface poses health risks. Dust storms and extreme temperature swings add to the difficulties. Despite these obstacles, progress is being made. Technologies for producing fuel, oxygen, and water from local resources are being tested. Habitats that can protect crews are being designed. International cooperation will likely play a key role in making human Mars missions a reality. Mars holds a special place in our collective imagination. It is close enough to be within reach, yet distant enough to be challenging. It offers the possibility of finding life, or at least evidence of past life, which would profoundly change our understanding of biology. It also serves as a potential destination for future human settlement, expanding humanity's presence beyond Earth. The transition from Mars to the asteroid belt marks a shift in the solar system's architecture. Beyond Mars, the influence of Jupiter becomes dominant. The giant planet's gravity prevented material in the region from coalescing into a single world, instead maintaining a scattered population of smaller bodies. This gravitational stirring explains why the asteroid belt exists at all. Without Jupiter, the material might have gathered into another rocky planet, leaving the region between Mars and Jupiter empty. As we leave Mars, we transition from the rocky inner planets to the realm of the gas giants. The asteroid belt lies between Mars and Jupiter, marking a boundary. This region contains millions of rocky bodies, ranging from tiny fragments to Ceres, a dwarf planet nearly 1,000 kilometers in diameter. The asteroids are remnants from the early solar system, material that never coalesced into a planet. Jupiter's gravity prevented that from happening, stirring the region and causing frequent collisions. Most asteroids orbit in a relatively flat plane aligned with the planets. However, some have highly elliptical or inclined orbits. Near-Earth asteroids occasionally pass close to our planet, and tracking them is important for planetary defense. Missions like OSIRIS-REx and Hayabusa have visited asteroids, collected samples, and returned them to Earth. These samples contain primitive material that has changed little since the solar system formed. Studying them provides clues about the composition of the early nebula and the building blocks of planets. The asteroid Bennu, visited by OSIRIS-REx, is a rubble pile held together by gravity rather than internal strength. Its surface is covered in boulders, with only a few smooth areas. The spacecraft collected a sample by briefly touching the surface, firing a burst of nitrogen gas to kick up loose material. The sample contained more material than expected, creating challenges for storage. The mission successfully returned the sample to Earth in 2023, providing scientists with pristine material to study. Preliminary analysis has revealed a variety of minerals and organic molecules, confirming that asteroids preserve ancient chemistry. Ceres is the largest object in the asteroid belt and the only one classified as a dwarf planet. NASA's Dawn spacecraft orbited Ceres from 2015 to 2018, mapping its surface and studying its composition. Ceres has a partially differentiated interior, with a rocky core and a mantle that may contain a significant amount of water ice. Bright spots on the surface, particularly in a crater, are deposits of sodium carbonate, likely brought to the surface by brines from below. These findings suggest that Ceres may have had a subsurface ocean in the past, and possibly still has liquid water at depth. The asteroid belt is not the densest region of the solar system. The space between individual asteroids is vast. Spacecraft can pass through without much risk of collision. Still, the sheer number of objects makes the belt a significant feature. It serves as a reservoir of material and a reminder that planet formation is not always tidy. Some asteroids share the orbits of planets, held in stable positions by gravity. The Trojan asteroids near Jupiter are a well-known example. Metal-rich asteroids are of particular interest for future resource extraction. Some contain high concentrations of iron, nickel, and precious metals like platinum. Mining these bodies could provide raw materials for space-based industry, though the technology and economics remain speculative. The concept represents a long-term vision for human expansion into the solar system. As we leave the asteroid belt, we approach Jupiter, the king of planets. It is the largest and most massive planet in the solar system, containing more than twice the mass of all other planets combined. Its gravity dominates the outer solar system, influencing the orbits of comets and asteroids. Jupiter is a gas giant, meaning it has no solid surface. The visible features are clouds in its upper atmosphere. Jupiter's atmosphere is composed mainly of hydrogen and helium, with traces of methane, ammonia, and water vapor. Winds reach speeds of hundreds of kilometers per hour, organized into bands of alternating light and dark zones. The light zones are regions of rising gas, while the dark belts are where gas descends. The interface between these bands creates powerful jet streams. The Great Red Spot is a massive storm that has been observed for at least 350 years. It is an anticyclonic vortex, meaning it rotates counterclockwise in the southern hemisphere. At its largest, the storm was more than twice the diameter of Earth, though it has been shrinking in recent decades. Despite this, it remains one of the most iconic features in the solar system. The storm's colour comes from complex organic molecules formed by sunlight interacting with atmospheric chemicals. The chemistry of Jupiter's atmosphere is complex and dynamic. Ammonia ice forms clouds at high altitudes, while deeper layers contain water ice and possibly liquid water droplets. Lightning has been detected, and thunderstorms on Jupiter can be enormous, dwarfing anything seen on Earth. The energy driving the weather comes partly from sunlight and partly from heat escaping from the planet's interior. Jupiter radiates more energy than it receives from the Sun, a remnant of its formation and ongoing gravitational compression. Jupiter rotates faster than any other planet in the solar system. A day on Jupiter lasts just under 10 hours. This rapid rotation causes the planet to bulge at the equator. It also generates a powerful magnetic field, the strongest of any planet. The magnetosphere extends millions of kilometers into space and traps high-energy particles. Radiation levels near Jupiter are intense enough to damage spacecraft electronics. Missions must be carefully shielded and follow trajectories that minimize exposure. Jupiter's aurora are among the most powerful in the solar system. They occur near the poles, where charged particles from the magnetosphere spiral down into the atmosphere along magnetic field lines. The particles collide with atmospheric gases, exciting them and causing them to emit light. The aurora on Jupiter are driven partly by the solar wind and partly by material ejected from the moon Io. Unlike Earth's aurora, which are intermittent, Jupiter's aurora are persistent and can be observed constantly. Jupiter's interior structure remains somewhat mysterious. Beneath the visible clouds lies a deep atmosphere that gradually transitions to liquid metallic hydrogen under immense pressure. At the centre, there may be a rocky core, though recent data from Juno suggests the core may be partially dissolved or diluted. The extreme conditions inside Jupiter are difficult to replicate in laboratories, making models uncertain. Studying Jupiter helps scientists understand not only our own solar system, but also the many giant exoplanets discovered around other stars. Jupiter has at least 95 confirmed moons, with more likely awaiting discovery. The four largest, discovered by Galileo in 1610, are called the Galilean moons. They are Io, Europa, Ganymede, and Callisto. Each is a world unto itself. Io is the most volcanically active body in the solar system. Tidal heating from Jupiter's gravity causes its interior to melt, driving continuous eruptions. Sulfur compounds give Io its colourful yellow and orange appearance. Plumes from the volcanoes can reach hundreds of kilometres above the surface. Io's volcanoes are not like those on Earth. The lava is hotter and more fluid, and some eruptions involve sulfur rather than silicate rock. The constant volcanic activity resurfaces Io quickly, erasing impact craters almost as soon as they form. This makes Io's surface one of the youngest in the solar system. The tidal heating that powers the volcanism comes from gravitational interactions with Jupiter and the other Galilean moons. As Io orbits, it is pulled and squeezed, generating heat through friction. This process is so intense that Io radiates more heat per unit area than any other body in the solar system. Europa is covered in a thick shell of ice. Beneath the ice, a global ocean of liquid water is thought to exist, kept warm by tidal heating. The ice surface shows cracks, ridges, and chaotic terrain, suggesting the shell is active. Europa is considered one of the best candidates for finding life beyond Earth. Future missions, including NASA's Europa Clipper, will study the Moon in detail, measuring the ice thickness and searching for plumes of water vapor. Europa's surface is relatively smooth and young, with few impact craters. This suggests that the ice is constantly renewed, either through upwelling from below or through fracturing and refreezing. Linear features called lineae crisscross the surface. These may form when the ice cracks and liquid or slushy water from below fills the gaps. The reddish-brown streaks visible on Europa's surface are thought to be salts or sulfur compounds, possibly delivered by radiation or brought up from the ocean below. If Europa's ocean is in contact with a rocky seafloor, hydrothermal vents could provide chemical energy for life. Much like vents on Earth's ocean floors support unique ecosystems. Ganymede is the largest moon in the solar system, bigger than the planet Mercury. It has its own magnetic field, the only moon known to possess one. The surface is divided into dark, heavily cratered regions and lighter, grooved terrain. Ganymede likely has a subsurface ocean as well, sandwiched between layers of ice. Callisto is heavily cratered and geologically inactive. Its surface is ancient, preserving a record of impacts over billions of years. Callisto may also harbour a subsurface ocean, though the evidence is less certain than for Europa and Ganymede. The smaller moons of Jupiter are equally fascinating. Amalthea, one of the inner moons, is irregularly shaped and reddish in colour. It orbits within Jupiter's main ring and may be a source of ring particles. Many of Jupiter's outer moons are thought to be captured asteroids or comets. They orbit in retrograde, meaning they move in the opposite direction to Jupiter's rotation. These moons are small and irregular, and their orbits are often highly inclined. Studying them provides clues about the early solar system and the process of gravitational capture. Jupiter has a faint ring system, discovered by Voyager 1-inch 1979. The main ring is composed of dust particles ejected from small inner moons by micrometeorite impacts. The ring is thin and difficult to see except when backlit by the sun. The particles in the ring are constantly being lost, either falling into Jupiter or being blown away by radiation pressure, so the ring must be continuously replenished. The existence of the ring highlights the dynamic nature of planetary environments. The Juno spacecraft has been orbiting Jupiter since 2016, studying its atmosphere, magnetic field, and interior structure. Juno's measurements have revealed that Jupiter's core may be larger and more diffuse than previously thought. The spacecraft has also captured stunning images of the polar regions, showing swirling cyclones arranged in geometric patterns. These observations are helping scientists understand the dynamics of the atmosphere and the planet's formation. Jupiter plays a crucial role in the solar system's architecture. Its gravity deflects comets and asteroids, reducing the number that enter the inner solar system. This protective effect may have been important for life on Earth, preventing excessive bombardment. However, Jupiter also occasionally sends objects inward, so the relationship is complex. The planet formed early in the solar system's history, possibly within the first few million years. Its presence influenced the distribution of material, creating the asteroid belt and shaping the orbits of other planets. Some models suggest Jupiter migrated inward and then back outward during its formation, a process that would have had dramatic effects on the inner solar system. Understanding Jupiter helps us understand the entire system's evolution. As we move beyond Jupiter, we encounter Saturn, the ringed jewel of the solar system. Saturn is the second largest planet, only slightly smaller than Jupiter in diameter, but much less massive. Like Jupiter, it is a gas giant composed mostly of hydrogen and helium. Its lower density means it would float in water if a sufficiently large ocean existed. Saturn's rings are its most striking feature. They extend hundreds of thousands of kilometers from the planet, but are remarkably thin, in places less than 10 meters thick. The rings are composed of countless particles of ice and rock, ranging in size from tiny grains to house-sized boulders. Each particle orbits Saturn independently, creating the appearance of a solid structure. The rings are divided into several main sections, labelled alphabetically in order of discovery. The A and B rings are the brightest and most visible from Earth. The Cassini division is a gap between them, caused by gravitational resonances with Saturn's moons. The rings are not permanent. They are likely only a few 100 million years old and are gradually being lost as particles spiral inward or are ejected. They may have formed from the breakup of a moon or a captured comet. The ring particles are mostly water ice, with some rocky material mixed in. Observations show that the particles are constantly colliding, grinding each other down over time. Moonlets, small embedded moons within the rings, create gaps and waves as they orbit. These features help scientists understand the dynamics of ring systems. Shepherd moons, which orbit just inside and outside certain rings, help confine the ring particles through gravitational interactions. The F ring, one of the narrower rings, is particularly dynamic, with braids and kinks that change over short timescales. Ring dynamics offer insights into processes that operate in other astrophysical disks, such as protoplanetary disks around young stars or accretion disks around black holes. The same physics of orbital mechanics, collisions, and gravitational interactions apply at different scales. By studying Saturn's rings in detail, scientists can test models that are difficult to observe elsewhere. The rings also provide a natural laboratory for understanding how particles aggregate or disperse under various forces. Saturn's atmosphere shows banded structure similar to Jupiter's, though the features are less distinct. Winds blow at high speeds, and occasional storms erupt, creating bright white spots visible from Earth. In 2010, a massive storm appeared in the northern hemisphere, encircling the entire planet before dissipating. Such storms seem to occur roughly every 30 years, coinciding with Saturn's seasons. The atmosphere of Saturn contains ammonia, ice clouds at higher altitudes, water ice clouds deeper down, and possibly droplets of liquid helium near the core. Lightning has been detected, and radio emissions suggest electrical activity is common. The exact mechanisms powering Saturn's weather remain under investigation, but the planet's rapid rotation and internal heat both play roles. Saturn has at least 146 confirmed moons, making it the planet with the most known satellites. Titan is the largest and the only moon in the solar system with a thick atmosphere. The atmosphere is mostly nitrogen, with traces of methane and other hydrocarbons. Titan's surface pressure is about 50% higher than Earth's. Thick haze obscures the surface, but radar and infrared observations have revealed lakes and seas of liquid methane and ethane near the poles. Channels that resemble riverbeds wind across the surface, carved by flowing hydrocarbons. Titan's weather includes methane rain, and seasonal changes affect the distribution of liquids. Beneath the surface, Titan likely has a subsurface ocean of water mixed with ammonia. Tidal measurements suggest the icy shell floats on a liquid layer. This makes Titan another candidate for hosting life, though any organisms would need to be very different from those on Earth. The chemistry is organic, rich, and energy sources exist in the form of sunlight and possibly tidal heating. The Cassini mission studied Titan extensively during multiple flybys and deployed the Huygens probe, which landed on the surface in 2005. Huygens returned images showing rounded cobbles and a flat plain, likely a dried lakebed. The data revealed a dynamic world shaped by processes familiar yet alien. Titan's thick atmosphere creates a greenhouse effect that warms the surface slightly, though temperatures still hover around -180 degrees Celsius. The atmospheric chemistry is complex, with methane acting similarly to water in Earth's hydrological cycle. Methane evaporates from the surface, rises into the atmosphere, condenses into clouds, and falls as rain. This cycle shapes the landscape, carving channels and filling lakes. The organic molecules created in Titan's atmosphere eventually settle onto the surface as a brownish haze, possibly accumulating into dunes. These dunes have been observed near the equator, shaped by winds into long parallel ridges. Enceladus is another moon of great interest. It is small, only about 500 kilometers in diameter, but extraordinarily active. Geysers near the South Pole shoot water vapor and ice particles into space, creating a plume visible from orbit. The material feeds Saturn's faint E-ring. The plumes originate from a subsurface ocean in contact with a rocky core. Hydrothermal vents on the ocean floor may provide chemical energy, creating conditions potentially suitable for life. Future missions could sample the plume material without landing, analyzing it for organic molecules and other signs of biological activity. Cassini flew through Enceladus's plumes multiple times, collecting samples directly. The analysis revealed water, salts, and organic molecules, including some that are considered building blocks of life. The discovery of molecular hydrogen in the plumes suggests hydrothermal activity, where water interacts with hot rocks on the ocean floor. On Earth, similar environments support thriving ecosystems independent of sunlight. If life exists in Enceladus's ocean, it could represent a second genesis, proving that life can arise independently in different environments. Other notable moons include Mimas, famous for a large crater that gives it a resemblance to a fictional space station. Iapetus has a two-toned appearance, with one hemisphere bright and the other dark, possibly due to material transfer from another moon. Hyperion is irregularly shaped and chaotically tumbling, its surface resembling a sponge. Each moon tells part of Saturn's story. The Cassini spacecraft orbited Saturn from 2004 to 2017, conducting one of the most successful planetary missions ever. It studied the rings in unprecedented detail, discovered new moons, and monitored the atmosphere and magnetic field. At the end of its mission, Cassini was deliberately sent into Saturn's atmosphere to avoid contaminating potentially habitable moons. The data from Cassini will be analysed for years, and the discoveries continue to reshape our understanding. Saturn's magnetic field is nearly aligned with its rotation axis, making it unusual among planets. The field is generated by metallic hydrogen in the interior, where pressure is so high that hydrogen behaves like a liquid metal. Aurora occur near the poles, where charged particles interact with the atmosphere. Studying these processes helps scientists understand planetary magnetic fields more broadly. Beyond Saturn lies Uranus, the first planet discovered with a telescope. William Herschel identified it in 1781, doubling the known size of the solar system at the time. Uranus is an ice giant, meaning it contains more water, methane, and ammonia than hydrogen and helium. Its mass is much smaller than Jupiter or Saturn, but still more than a dozen times Earth's mass. Uranus has a pale blue-green colour due to methane in its atmosphere. Methane absorbs red light, leaving the blue-green wavelengths to reflect back. The most unusual feature of Uranus is its extreme axial tilt. The planet rotates on its side with an axial tilt of about 98 degrees. This means its poles alternately point toward the Sun during its 84-year orbit. For about 42 years, one pole experiences continuous sunlight while the other is in darkness. Then the situation reverses. This produces extreme seasonal variations and unusual atmospheric dynamics. The cause of the tilt is thought to be a massive collision early in the planet's history, which knocked Uranus onto its side. The collision that tilted Uranus may also have scattered debris that eventually formed its moons. The moons orbit in the planet's equatorial plane, which is nearly perpendicular to the plane of the solar system. This alignment suggests they formed after the tilt occurred. The impact may have also affected the planet's interior structure, mixing materials and creating a less distinct layering than found in Jupiter or Saturn. The seasons on Uranus are unlike anywhere else. During the northern summer, the North Pole points almost directly at the Sun for 21 Earth years. The South Pole remains in darkness during this entire time. Then, as the planet moves along its orbit, the equatorial region faces the Sun, and both poles experience day and night cycles. Eventually, the South Pole points toward the Sun for its own 21-year summer. This extreme seasonal cycle affects atmospheric dynamics in ways that are still being studied. Voyager 2 is the only spacecraft to have visited Uranus, flying past in 1986. It revealed a relatively featureless atmosphere with few clouds or storms. The planet appeared calm, though later observations with advanced telescopes have detected more activity. Winds blow at hundreds of kilometers per hour, and occasional storms have been observed. The rings of Uranus were discovered in 1977 during a stellar occultation. They are dark and narrow, composed of particles that are likely coated with radiation-processed organics. Uranus has 13 known rings, much fainter than Saturn's. The planet also has at least 27 moons, most named after characters from the works of William Shakespeare and Alexander Pope. The 5 largest moons are Miranda, Ariel, Umbriel, Titania, and Oberon. Miranda is the smallest of the 5, but geologically the most interesting. Its surface is a patchwork of different terrains, including ancient cratered areas and younger, grooved regions. Steep cliffs rise several kilometers, and the overall appearance suggests a complex history, possibly involving tidal heating or a major impact. Ariel has long valleys and signs of past cryovolcanism, where water or ammonia lavas flowed. Umbriel is darker and heavily cratered, with one bright ring of uncertain origin. Titania and Oberon are the largest, both heavily cratered but showing evidence of past geological activity. Uranus has a magnetic field, but it is tilted about 60 degrees from the rotation axis and offset from the center. This unusual geometry creates a lopsided magnetosphere that wobbles as the planet rotates. The field's origin is thought to lie in a layer of ionized water and ammonia deep in the interior, rather than a metallic hydrogen layer, as in Jupiter and Saturn. Neptune is the outermost of the classical planets, discovered in 1846 through mathematical predictions rather than direct observation. Irregularities in Uranus's orbit suggested another planet's gravity was influencing it. Calculations pointed to a specific region of the sky, and Neptune was found close to the predicted position. It is similar in size and composition to Uranus, another ice giant. Its atmosphere is a deeper blue than Uranus, also due to methane, but with an additional component that remains unidentified. Neptune is remarkably active despite being so far from the Sun. The Great Dark Spot, a A storm system observed by Voyager, 2 inches, 1,989, was comparable in relative size to Jupiter's Great Red Spot. However, when the Hubble Space Telescope observed Neptune a few years later, the spot had disappeared. New storms have since been detected, showing that the atmosphere is dynamic. Winds on Neptune are the fastest in the solar system, exceeding 2,000 kilometers per hour. The energy driving these winds is a mystery, as Neptune radiates more heat than it receives from the Sun. Internal heat left over from formation or ongoing processes, like the settling of heavier elements, may provide the energy. The internal heat source in Neptune and Uranus is a subject of ongoing research. Unlike Jupiter and Saturn, which have clear internal heat signatures from gravitational compression and slow cooling, the ice giants present a puzzle. Their interiors may be differentiated in ways that create unusual thermal profiles. Some models suggest that precipitation of materials like carbon in the form of diamonds could release gravitational energy, contributing to the heat budget. These processes remain speculative, but highlight how much we still have to learn about these distant worlds. Neptune has at least 16 known moons. Triton is by far the largest, accounting for more than 99% of the mass orbiting Neptune. Triton is unusual because it orbits in the opposite direction to Neptune's rotation, a retrograde orbit. This suggests Triton was captured from the Kuiper Belt, likely a dwarf planet that was pulled in by Neptune's gravity. The capture process would have been violent, heating Triton's interior and possibly destroying other moons. Triton is geologically active. Voyager 2 observed geysers of nitrogen gas erupting from the surface, reaching several kilometers high. The surface is young, with few impact craters. It shows a variety of terrains, including frozen nitrogen plains, ridges, and a region called the cantaloupe terrain, with dimpled texture. Triton has a thin atmosphere and a faint haze layer. Beneath the surface, a subsurface ocean may exist, kept liquid by tidal heating as Triton's orbit slowly circularizes. Triton is gradually spiraling inward due to tidal forces. In tens of millions of years, it will cross Neptune's Roche limit and break apart, possibly forming a ring system more spectacular than Saturn's. For now, Triton remains one of the most intriguing moons in the solar system, a captured world with a complex past and an uncertain future. Neptune's rings are faint and clumpy, with arcs of denser material. The rings are composed of dark particles, and their structure is influenced by small inner moons. Neptune's magnetic field is also tilted and offset, similar to Uranus. The field geometry creates a complex magnetosphere that interacts with the solar wind in unusual ways. The ice giants, Uranus and Neptune, represent a class of planets common in the galaxy. Many exoplanets discovered around other stars fall into this category, making these two worlds important templates for understanding planetary diversity. Despite their distance and the difficulty of studying them, they hold clues about planet formation, atmospheric dynamics, and interior processes. Future missions to the ice giants are being planned, with proposals for orbiters and atmospheric probes that could revolutionize our understanding. Beyond Neptune lies the Kuiper Belt, a region of icy bodies extending from about 30 to 50 astronomical units from the Sun. The Kuiper Belt contains thousands of known objects, and likely millions more await discovery. These are remnants from the solar system's formation, icy planetesimals that never assembled into a full-sized planet. Pluto is the most famous resident of the Kuiper Belt. Once considered the 9th planet, it was reclassified as a dwarf planet in 2006 after the discovery of other similar-sized objects in the region. Pluto is about 2/3 the diameter of Earth's moon and has a complex surface with varied terrain. NASA's New Horizons spacecraft flew past Pluto in 2015, providing the first close-up images. The encounter revealed a world far more dynamic than expected. Sputnik Planitia, a vast plain of frozen nitrogen, dominates one hemisphere. The nitrogen ice appears to undergo convection, with cells rising and sinking over timescales of thousands of years. Mountains of water ice rise several kilometers, comparable to the Rockies. Pluto's surface shows a variety of colors, from white nitrogen ice to reddish organic compounds called tholins, formed by radiation processing of methane. Pluto has a thin atmosphere composed mostly of nitrogen, with traces of methane and carbon monoxide. The atmosphere is slowly escaping into space, forming a faint tail. As Pluto moves farther from the Sun in its elliptical orbit, the atmosphere freezes out onto the surface, only to sublimate again when it returns closer. Pluto has 5 known moons. Charon is the largest, about half Pluto's diameter. The two are so close in size that they orbit a common center of mass located between them, forming a binary system. Charon's surface is less varied than Pluto's, with large areas of water ice and a reddish polar cap, possibly formed by the capture of escaping atmospheric material from Pluto. The smaller moons, Styx, Nix, Kerberos, and Hydra, are irregularly shaped and thought to have formed from debris ejected during a collision that created Charon. Other notable Kuiper Belt objects include Eris, Makemake, and Haumea. Eris is slightly smaller than Pluto, but more massive. Its discovery played a key role in the debate that led to Pluto's reclassification. Makemake is bright and lacks a substantial atmosphere. Haumea is elongated due to rapid rotation, spinning once every 4 hours. It has 2 small moons and a ring system, the first ring discovered around a distant icy body. These objects help us understand the diversity of the outer solar system. They are time capsules, preserving material and conditions from the solar system's infancy. Studying them provides insights into how planets formed and how the architecture of the system evolved. The Kuiper Belt is home to objects caught in orbital resonances with Neptune. These resonances occur when an object's orbital period is a simple fraction of Neptune's period. Pluto, for example, is in a 3:2 resonance, completing 2 orbits for every 3 of Neptune's. This resonance protects Pluto from close encounters with Neptune, even though their orbits cross. Other objects are in 2:1 or 5:2 resonances. These resonant populations provide clues about how Neptune migrated outward during the early solar system, sweeping objects into stable orbits as it moved. The scattered disk extends beyond the Kuiper Belt and contains objects with highly elliptical or inclined orbits. These objects were likely scattered outward by gravitational interactions with Neptune during the early solar system. Sedna is one such object, with an orbit that takes it far beyond the Kuiper Belt. Its origin remains uncertain, and it may provide clues about the conditions in the outer reaches of the protoplanetary disk, or even interactions with passing stars. The discovery of these distant objects has reshaped our understanding of the solar system's structure. The region beyond Neptune is not empty, but filled with a population of icy bodies. Some of these objects have orbits that bring them close to the Sun, becoming comets. Others remain in the distant cold, barely illuminated by the Sun's faint light. The diversity of sizes, orbits, and compositions suggests a complex history of formation and dynamical evolution. Comets originate primarily from 2 regions. Short-period comets come from the Kuiper Belt, while long-period comets come from the Oort cloud. Short-period comets have orbital periods less than 200 years and tend to stay close to the plane of the solar system. Long-period comets can have periods of thousands or even millions of years and arrive from any direction. When a comet approaches the Sun, heat causes ices to sublimate, releasing gas and dust. This forms a glowing coma around the nucleus, and often two tails. The iron tail is pushed directly away from the Sun by the solar wind, while the dust tail curves along the orbit. Comets are fragile and sometimes break apart during close passes to the Sun. Missions to comets have provided detailed views of these ancient bodies. The Rosetta mission orbited comet 67P Churyumov-Gerasimenko for 2 years, deploying a lander named Philae. Rosetta observed the comet as it approached the Sun, documenting changes in activity and mapping the surface in detail. The nucleus is irregularly shaped, resembling a rubber duck, and its surface is dark and rugged. Rosetta detected complex organic molecules and water with a different isotopic ratio than Earth's oceans, suggesting that asteroids, rather than comets, delivered most of Earth's water. The Oort cloud is the outermost part of the solar system, a vast spherical shell of icy bodies extending thousands of astronomical units from the Sun. It is named after Jan Oort, who proposed its existence in 1950 to explain the origin of long-period comets. The Oort cloud has never been directly observed. Its members are too small and too far away to see with current technology. However, the orbits of long-period comets point back to this region. The cloud is thought to contain trillions of objects, with a total mass several times that of Earth. The Oort cloud formed from material scattered outward by the giant planets during the solar system's early chaotic phase. Objects that ventured too close to Jupiter or Saturn were flung outward, some escaping the solar system entirely and others settling into distant orbits. The outer edge of the Oort cloud marks the boundary of the Sun's gravitational influence. Beyond this lies interstellar space. The transition is not sharp but gradual, as the Sun's gravity weakens and the influence of nearby stars becomes comparable. Occasionally, a passing star or gravitational perturbations from the galaxy disturb the Oort cloud, sending comets inward. These visitors become visible only briefly before returning to the darkness. Some may be deflected by the planets into shorter orbits, joining the ranks of short-period comets. Others may be ejected entirely, becoming interstellar wanderers. The Oort cloud is a reservoir of primordial material, a remnant of the disk from which the planets formed. It preserves conditions from the solar system's birth, waiting in frozen silence. From tiny comets glimpsed in the sky, we infer this massive unseen sphere surrounding everything we know. The realization transforms imagination into science, teaching us about scales far greater than everyday life suggests. To pause here is to stand at the invisible edge of the Sun's gravitational reach, where comets drift in silence. The sphere around us is immense yet delicate, filled with frozen archives awaiting chance encounters that might send them sunward. From this vantage, the journey will continue past this halo toward the stars and into the questions that lie beyond. The story is not finished, because beyond the cloud lies the unknown, and the chapters yet to come will carry us outward still. Now we turn toward the future, where exploration becomes less about the places we have visited and more about how far we might eventually travel and what we might ultimately discover. The solar system we have traced is already vast, filled with planets, moons, and distant clouds of ice. Yet the questions we confront extend even farther. In this final part of the journey, we consider missions, technologies, and the possibility of moving beyond the Sun's domain into the realm of other stars. The future is unwritten, but every mission launched and every concept explored pushes the boundary outward a little more. Human exploration has always been linked to vision and the ambitions set for each generation. From the Apollo missions to the Moon to rovers traversing the surface of Mars, we have steadily expanded our reach. Today, preparations are underway for the Artemis program, for crewed Mars missions, and for expeditions to icy moons where life might exist or where new science awaits. Yet beyond these concrete plans lies the idea of interstellar travel, where spacecraft might move faster and venture farther than anything attempted before. The challenge is immense, but the drive to explore is older than modern technology, older even than recorded history itself. The Artemis program represents humanity's return to the Moon after more than 50 years. Unlike Apollo, which aimed to demonstrate capability during the Cold War, Artemis seeks to establish a sustainable presence. The program includes building the Lunar Gateway, a space station that will orbit the Moon and serve as a staging point for surface missions. Astronauts will land near the lunar South Pole, where water ice has been detected in permanently shadowed craters. This ice could be mined and processed into drinking water, breathable oxygen, and hydrogen fuel for rockets. The technologies developed for Artemis will directly support future Mars missions. Mars missions present challenges of a different order. The distance means communication delays of several minutes each way, making real-time control from Earth impossible. Astronauts will need to make decisions independently. The radiation environment in deep space and on the Martian surface is harsher than anything experienced in low Earth orbit. Shielding and possibly pharmaceutical countermeasures will be necessary. Psychological challenges also loom large. Crews will be isolated for years, living in confined spaces with limited contact with home. Selecting and training crews for such missions requires careful attention to both technical skills and interpersonal dynamics. Producing resources on Mars using local materials, a concept called in situ resource utilization, is critical for making missions feasible. Transporting everything from Earth would be prohibitively expensive. Instead, technologies are being developed to extract water from the soil, produce oxygen from atmospheric carbon dioxide, and manufacture fuel from Martian resources. The Perseverance rover's MOXIE experiment has demonstrated that oxygen production is possible. Scaling up these processes to support human crews is the next step. The concept of terraforming Mars, transforming it into a more Earth-like world, has been discussed for decades. Proposals include releasing greenhouse gases to warm the planet, melting the polar ice caps, and thickening the atmosphere. If successful, this could eventually create conditions suitable for liquid water and perhaps even breathable air. However, the process would take centuries or millennia and require vast amounts of energy and resources. Ethical questions also arise. If Mars harbours any native life, even microbial, should we alter the planet in ways that might destroy it? These debates will continue as our capabilities grow. Robotic missions remain the leading edge of discovery. Each probe carries sensors and instruments, and each travels farther from home than the last. Voyager 1 and Voyager 2 are now interstellar messengers, their signals faint but still returning whispers from outside the heliosphere, the bubble of space dominated by the solar wind. These craft carry golden records engraved with sounds, music, and messages intended for anyone or anything that might one day encounter them. Though the chance of discovery is small, the records represent human hope encoded into metal, drifting between the stars. The heliosphere itself is a dynamic structure shaped by the solar wind and the pressure of the interstellar medium. The boundary, called the heliopause, is where the solar wind's influence ends and interstellar space begins. Voyager 1 crossed this boundary in 2012, followed by Voyager 2 inches 2018. The data sent back revealed that the transition is not abrupt, but a complex region with fluctuating conditions. Understanding the heliosphere helps protect spacecraft and astronauts from cosmic radiation, as the solar wind provides some shielding from high-energy particles originating outside the solar system. New concepts are being studied, including solar sails driven by light. These sails catch photons and accelerate gradually to high velocities. The idea is simple, yet powerful, using the pressure of starlight for propulsion without needing fuel once deployed. The Breakthrough Starshot initiative proposes sending tiny spacecraft toward Proxima Centauri, the nearest star system. With powerful laser arrays providing the push, these probes might reach their destination in decades rather than millennia. Such ideas sound ambitious, but they reflect a growing understanding that technology may someday make interstellar distances less daunting. Solar sails have been tested in space. The Japanese Ikaros spacecraft demonstrated controlled solar sailing in 2010. NASA's LightSail 2, launched in 2019, successfully raised its orbit using sunlight alone. These missions proved the concept works, paving the way for more ambitious applications. A solar sail could be used to reach the outer solar system more quickly than conventional propulsion, or to maintain a position offset from the Sun for observing the heliosphere's structure. Nuclear propulsion is another possibility, whether through fission or fusion. These engines release far more energy than chemical rockets, potentially shortening travel times to the outer planets to a matter of months, or journeys to stars to centuries instead of tens of thousands of years. Concepts like Project Orion once imagined detonating small nuclear explosions behind a spacecraft, propelling it forward step by step. Though controversial, the underlying physics is sound. The barriers are social, political, and technical, not conceptual. Fusion propulsion holds particular promise. Fusion reactions release more energy per unit mass than fission and produce less radioactive waste. The challenge is achieving controlled fusion in a compact, lightweight engine suitable for spacecraft. If this hurdle can be overcome, fusion-powered ships could travel at a significant fraction of the speed of light, making interstellar missions within a human lifetime conceivable. Research into fusion energy for terrestrial use also benefits space propulsion, as advances in one field inform the other. Generation ships represent another approach to interstellar travel. These would be massive spacecraft designed to support multiple generations of humans during journeys lasting centuries. The ship would be a self-contained world with ecosystems, agriculture, and manufacturing capabilities. Children would be born, live, and die aboard the ship, never seeing Earth or the destination. The social and ethical implications are profound. How would governance work? How would knowledge and culture be preserved across generations? These questions touch on fundamental aspects of human nature and society. The desire to travel outward is not solely about science. It also touches on survival and the long-term future of humanity. Earth remains our only home, but its resources are finite, and its climate is not infinitely stable. To ensure humanity can endure across the ages, we must eventually look beyond. Colonies on Mars, orbital stations, and lunar bases represent first steps. Each builds the skills and technologies needed for larger endeavors. In this sense, exploration is not a luxury, but a necessity, written into our nature as deeply as curiosity itself. Establishing a self-sustaining colony on Mars or elsewhere requires solving numerous technical and logistical problems. Food production in closed environments, recycling of air and water, and manufacturing of spare parts and tools all need reliable systems. Psychological and social structures must support communities living far from Earth, possibly for generations. These challenges mirror those faced by early human migrations across Earth, but with the added difficulty of hostile environments and no possibility of resupply if something goes wrong. As we imagine these futures, we also consider what we might find. Will we discover life in the subsurface oceans of icy moons? Will we detect signals from other civilizations? Or will we encounter only silence? If life is found on moons like Europa or Enceladus, it will change our understanding, proving that biology is not rare or unique to Earth. If signals from another civilization are ever detected, the impact would be profound, forcing humanity to reflect on its place in the cosmos. Yet even if we find only silence, the search itself gives meaning, framing our existence within the vast stage of the universe. The search for extraterrestrial intelligence, known as SETI, has been ongoing for decades. Radio telescopes scan the sky for signals that might indicate technological activity. So far, no confirmed signals have been detected, but the search continues. New techniques are being developed, including searching for laser pulses and looking for signs of large-scale engineering projects around other stars. The absence of detected signals raises questions. Are we alone? Are civilizations rare? Do they exist but remain silent, or are we simply not looking in the right way? These questions drive ongoing research and philosophical reflection. The Fermi paradox asks, why, if intelligent life is common in the galaxy, we have not detected any evidence of it? Various explanations have been proposed. Perhaps intelligent civilizations are rare. Perhaps they exist but are too far away for us to detect. Perhaps they exist but choose not to communicate. Perhaps they destroy themselves before achieving interstellar capability. Each possibility has implications for how we think about our own future and our place in the universe. The cosmos beyond our sun is endless, with billions of stars, billions of planets, and uncounted numbers of potential worlds. Astronomers now regularly discover exoplanets, detecting their presence through subtle changes in starlight. We know of hot Jupiters orbiting close to their stars, rocky Earth-sized worlds, and super-Earths located in habitable zones where liquid water might exist. Each planet is a candidate for further study. Future telescopes will analyze their atmospheres, searching for signs of water vapor, oxygen, or methane. The question of whether we are alone echoes through every observation, silent yet heavy with implications. Exoplanet discoveries have revealed that planetary systems come in a bewildering variety. Some stars host multiple planets in tight orbits. Others have planets in highly elliptical paths. Binary star systems can have planets orbiting one star or both. The diversity challenges simple models of planet formation and forces astronomers to consider a wide range of processes. Each discovery adds to the catalogue of known worlds, and each one brings new questions. If life is common in the universe, then the cosmos is filled with neighbours, some distant and some relatively near. If life is rare, then we may be the only voice in the darkness, carrying a unique responsibility for consciousness and awareness. Either answer is profound, shaping philosophy, culture, and the direction of future generations. In the far future, humanity might reach the Oort cloud physically, building habitats on comets or other icy bodies. Resources there could provide water, fuel, and raw materials, sustaining communities at the edge of the sun's reach. Settlements may develop where sunlight is faint, under protective domes or buried within ice, surviving with fusion power or energy harvested from other sources. From that distant foothold, stepping into true interstellar space would be a natural progression, one stage in a migration spanning thousands of years. Building habitats in the outer solar system will require new architectural approaches. Structures must withstand the cold and provide radiation shielding. Power generation will rely on nuclear sources as solar panels become impractical at such distances. Communities might be entirely underground, carved into the ice of comets or moons, with only minimal surface installations. Life in these environments will be fundamentally different from life on Earth, requiring adaptation and resilience. Yet the journey is not only physical, it is also a transformation of perspective, a way of seeing ourselves differently. To contemplate the solar system as one interconnected home shifts national boundaries into minor details on a planetary surface. To imagine stars as destinations, rather than decorative points in the night sky, changes our sense of what is possible. The deep frontier is as much about expanding the mind as it is about advancing machines. It requires a shift of vision as much as a change of location. Even today, telescopes search for biosignatures in the atmospheres of distant planets. Instruments measure chemical compositions, hunting for imbalances that might indicate the presence of life. Oxygen and methane in the same atmosphere, for instance, could suggest biological activity. Future missions like LUVOIR or HABEX may capture images of pale blue dots orbiting other stars, worlds similar to Earth. The day such an image is confirmed will reshape our sense of place in the universe. It will no longer be a question of if, but of where and how many. That moment will carry weight far beyond the realm of science, touching culture and sparking the imagination of every person on Earth. Detecting biosignatures requires extremely sensitive instruments. The light from a planet is millions or billions of times fainter than the light from its star. Blocking out the star's glare while capturing the planet's faint signal is a major technical challenge. Coronagraphs and starshades are being developed to address this. Once a planet's light is isolated, spectroscopy can reveal the composition of its atmosphere. Patterns of absorption and emission at specific wavelengths indicate the presence of different molecules. In the end, the universe is not only a collection of facts and data, it is also a story we tell ourselves about meaning and connection. Exploration provides continuity, a thread linking past wanderers with future travelers. It reminds us that the same curiosity that led early humans to light fires in caves now drives spacecraft toward distant stars. The thread is unbroken, running through every human age, carrying us farther with each step. The solar system is now complete in our mental map, though not in every detail. Moons and belts still hold mysteries waiting to be uncovered. The giant planets continue to reveal new storms and magnetic phenomena, while small bodies preserve memories of the distant past. Every object studied adds depth and texture. Every mission expands our understanding of scale and complexity. The whole grows richer with each discovery. Yet the larger story remains open because the future lies beyond, across distances we have not yet touched. To close this narration is not to end the story, but to acknowledge its continuation into the time ahead. We stand on one planet, yet our instruments and machines have touched moons, asteroids, comets, and even interstellar space. Every generation extends the line of exploration, and future generations will carry it still farther. This series of chapters has been only the beginning, the first steps into an endless frontier. We began with the structure of atoms and the birth of stars, with heat and motion and the forces that shaped worlds. We end with horizons stretching outward and hope for what lies ahead. The journey of the cosmos is far greater than any single species can encompass. Yet our voice now joins the chorus. If the universe is silent, our words still add sound to the void. If it is filled with other voices, we add harmony to the music. Either way, to venture outward is to honor the gift of awareness itself. So we rest here at the edge of the known, where the Oort cloud fades into darkness and the stars begin their true dominion. The path forward is uncharted. Yet the first markers have been placed in probes that drift beyond the heliosphere, in telescopes that peer across light years, and in the ideas that guide us. We understand now that boundaries are illusions, and that systems stretch outward until they merge seamlessly with others. To end here is to acknowledge continuity, not finality. Exploration has no true ending, only new beginnings that stretch into the infinite ahead.